Hello, pre-calculus students. This is still section 6.1 notes. This is part 2. The next thing we're going to talk about is the length of a circular arc in the unit circle. Okay. So first of all, it's important to know what we're talking about here. The length of a circle arc is really a part of the circumference of a circle. So if we look at our picture here of our circle, and again, we could think of this as being the unit circle, like so. We've got this angle here. We can call it whatever we want. We'll just call our angle theta. We know that this is the radius of our circle as well as the initial side of our angle. But when we talk about the length of a circular arc, what we're really talking about is this distance right here along the outside of the circle. So we know that the circumference of any circle is 2 pi r, circumference of the unit circle just 2 pi because radius is 1. So our arc length here, which is what we call S, that's just the name for it, is going to be a fraction of our circumference. So S would be equal to theta over 2 pi, that's the fraction part, times our circumference. So that means that we can develop this formula for the arc length of a circle. It would be that our arc length, the arc length of a portion of an angle of our circle. So the arc length S is equal to theta divided by 2 pi times the circumference of our circle, which is 2 pi r. And so when you look at this formula, when we multiply straight across the top and straight across the bottom, the 2 pi's cancel out, so we just end up with theta times r. So our formula, S, or our arc length, is going to be equal to our radius times theta, where r is the radius of the circle, S is the arc length, and theta is the central angle. And it's really important to note that for this formula, theta is always in radians. So you know what that means, right? If it's not given in radians, you need to convert it to radians before you plug it into this formula. If we look at our example here, it says to find the length of an arc of a circle with a radius of 14, so not the unit circle, right? Because it doesn't have a radius of 1, it has a radius of 14 inches that subtends a central angle of 30 degrees. We could draw a little picture. It's not necessary, but you know, we like to draw pictures. So here's our circle. Here's our angle of 30 degrees. So we're looking for that little distance right there, that little arc length. Here's the given information. We know that the radius of this circle is 14 inches, and we know that the central angle is 30 degrees. But remember, our formula is in radians. Fortunately for us, that's a nice one, so we don't even have to do any multiplying to convert it. 30 degrees is equivalent to pi over 6 radians. If we use our formula, S is equal to R times theta, that means that our arc length would be equal to 14 inches times pi over 6. In terms of pi, this would be 7 pi over 3 inches, or if we grab our calculators and we multiply 7 times pi divided by 3, it's going to be 7.33 inches, which maybe makes a little bit more sense when we're talking about length. As well as finding arc length, we can also find the area of a sector of a circle. So here's our picture. When we're talking about the area of a sector, we are actually talking about finding the area of this piece of the pie here. So obviously, when we look at our picture, the area of a circle is a part of the area of a circle. Some known facts. We know that the area of any circle is equal to pi times its radius squared. So if we're trying to find the area of a sector, we're trying to find a fraction of the area of a circle, right? So again, that fraction is theta divided by 2 pi times the area of the circle. So if we are going to, we're just going to call that little sector A there. So if we're trying to find the development of our formula for that area A, that's going to be equal to theta divided by 2 pi times pi r squared. So again, when we multiply across the top and across the bottom, our pi's are going to cancel out. So our formula for our sector becomes 1/2, because the 2 is on the bottom, r squared theta. So you could write that two ways. You could either write it just like that, 1/2 r squared theta, or you could write it as r squared theta divided by 2. Doesn't matter. It's exactly the same. Okay. And in this formula, r is the radius of the circle. And that can be given in any units, so you have to pay attention to what the units are so that you know how to report your answer. A is the area of the sector, and theta is the central angle. And just like the last formula, it's really important. Theta is always in radians. So again, if theta is not given in radians, it'll be your job to convert it to radians. For our last example, we're going to find the area of a sector of a circle with a diameter of 16 centimeters, that subtends a central angle of 2 pi over 5. Here's our given information. We know that the diameter of our circle is 16 centimeters, but remember our formula has radius in it. If our diameter is 16 centimeters, that means that our radius is going to be 8 centimeters. And we know that the central angle of our circle is 2 pi over 5. The nice thing is it's been given to us in radians, so we don't need to convert it. Oops, sorry about that. All right, so all we have to do is plug our information into our equation. We know our equation is area is equal to 1/2 r squared theta, area of our sector here. So 1/2 times 8 squared times 2 pi divided by 5. So when we do our math here, and again, the 2 on the bottom is going to cancel that 2 on the top in this particular problem. 8 squared is 64. So we end up with 64 pi over 5. Since the units on our radius were centimeters, then the area of our sector here would be in centimeters squared. But again, 64 pi over 5 doesn't really mean a lot to us. So if we grab our calculator and we multiply 64 times pi divided by 5, that tells us that our area is 40.2 centimeters squared.